Good morning to everyone. My name is Ashish Kumar Singh. I am working as an assistant professor in IIMT College of Engineering, Greater Noida. Today, I will discuss about three-phase induction motor in this online lecture. This lecture includes various. The contents of this lecture is first we will discuss about the introduction of three-phase induction motor. After discussing introduction of three-phase induction motor, we will discuss about the construction of three-phase induction motor. And then thereafter, we will discuss about working principle of three-phase induction motor and which principle it is based and how it works. Then thereafter, we will discuss about the slip, what is slips, and what are the various slip region and how three-phase induction motor works in slip region, and then thereafter we will discuss about torque slip characteristics. In this topic we will discuss about the what are the torque slip characteristics of three-phase induction motor and how three-phase induction motor behaves at different slip region. Then thereafter we will discuss about the advantages of three-phase induction motor, and after discussing the advantages of three-phase induction motor, we will discuss about the disadvantages of three-phase induction motor, and at the end, we will discuss the application where it is used, three-phase induction motor. So, let's start our topic. Introduction, three-phase induction motor are the most common machine used in industries. Why it is used in industries most commonly? Because of its simple design, rugged construction, low price, and easy maintenance. These are the certain advantages due to which three-phase induction motor are commonly used in industry. And then the next advantage due to which it is used in three-phase industries is its wide range of power rating. It is available from fractional of horsepower to the 10 mega up to 10 megawatt of powers. And next, the three-phase induction motor essentially runs at constant speed from zero to full load. This is the another advantage due to which it is widely used in three industries. So let us discuss about the construction of three-phase induction motor. As we know that every machine has two parts. One is stator and another is rotor. Same three-phase induction motor has two main parts. The first part is called stator. What is stator? A stationary part of the motor is known as stator. Mainly, it includes outer frame and yoke. It consists, so stator consists of a steel frame that support a hollow cylindrical core in which three-phase stator winding is placed, and the core constructed from stacked lamination having number of slots providing space for stator winding. Why it is constructed from stacked lamination? As we to reduce eddy current losses, as we know that eddy current loss mainly depends on frequency, square of frequency and square of thickness. So we can reduce eddy current loss by using thin laminated stacks of thin laminated sheet instead of solid core. So the stator core mainly constructed from stacked lamination. And what is the purpose of stator? The stator of electrical machine serve two purpose. First purpose is main purpose is to provide return path for the flux, and second to provide to support stator winding and rotor, and it also protect stator winding and internal circuitry from outer harsh environment. And the second part of the three-phase induction motor is rotor. So when we are talking about the rotor, what is rotor? Rotor is a revolving part of the motor It composed of punched lamination stacked to create a series of rotor slots, providing space for the rotor winding. There are two types of rotor winding mainly used in three-phase induction motor. First type of rotor used is called wound rotor. In this type of rotor, we normally place three-phase rotor winding that is made up of insulated wire similar to the winding on the stator on the rotor slots, and mainly in at rotor we generally provide we generally connect a rotor winding in star connection. And second type of rotor that is used in three-phase induction motor is squirrel cage rotor. In this type of rotor, uh, we placed a solid bar of aluminum or copper conductor inside the rotor slots, and these uh, conductors are short circuited at the ends of at both ends of the rotor circuits. So this squirrel cage rotor is all is mainly used for low starting purpose because we do not connect external resistance to the rotor winding to to increase its starting torque. So what is squirrel cage rotor? Here in this picture we saw the constructional diagram of squirrel cage rotor. A squirrel cage rotor is the rotating part of the common squirrel cage induction motor. In this picture we see that the aluminum bars are placed in the rotor slots of that is cut on the outer periphery of the rotors, and these rotor conductors are short circuited at the both end with the help of end ring. So it consists of cylinder of steel lamination with aluminum or copper conductor embedded in its surface. And second rotor that is used is wound rotor motor. It is this type of rotor is also known as slip ring rotor because three slip rings are placed on the shaft of the rotor uh, on which three-phase windings are connected. So this wound rotor is also known as slip ring rotor. The rotor winding are connected through slip ring to the external resistance to increase starting torque as per our requirement. And in this type of motor, we generally used we generally place three-phase rotor winding on the rotor slots and that are connected in star configuration. It can be started with low inrush current by inserting high resistance into the rotor circuit. What is inverse current? At the time of starting, when we start three-phase induction motor, the back EMF on the rotor motor is zero. So at the time of starting, induction motor takes high starting current that is called inrush current, and that is up to 4 to 8 times higher than its rated current. So to reduce that high inrush current, we are using high resistance in the rotor circuit. With the help, we connect high resistance into the rotor circuit with help of slip ring. This is the construction diagram of three-phase induction motor where we see that uh, this is the terminal box where we connect three-phase AC supply, and this is the stator outer parts of the motor that is known as stator, and then is there inside the outer frame we are having a stator winding that is placed on inner periphery of yoke, and there is a rotor. So after discussing the construction diagram of three-phase induction motor, we will discuss about the principle of operation on which principle three-phase induction motor work. As we discussed in earlier lecture, three-phase induction motor works on Faraday's law of electromagnetic induction, or it works on transformer action. In transformer, uh, we studied about the transformer principle, that is Faraday's law of electromagnetic induction. And what does it say? When a mag when a conductor moves in a magnetic field, conductor cuts magnetic line of forces, and due to the change in flux with respect to time to the conductor, an EMF is induced on the conductor. That is called Faraday's law of electromagnetic induction. And generally, transformer works on Faraday's law of mutual induction. So, same as three-phase induction motor also works on Faraday's law of mutual induction, or we can simply say that transformer action. If we are able to move secondary winding of transformer, we are able to rotate the secondary winding of transformer, then transformer will work as a three-phase induction motor. So we can say that a three-phase induction motor is generally a rotating transformer. So, principle of operation, when we are discussing about the principle of operation, we normally place three-phase stator winding on stator, and when we connect three-phase AC supply to the three-phase stator winding, a rotating magnetic field is produced in the air gap that is present between stator and rotor. This rotating magnetic field rotates in space with speed that is called synchronous speed, and it is indicated denoted by ns, and it is given by the formula ns equals to 120 f upon p, where f is the supply frequency and p is the number of poles, and ns is called synchronous speed and its units is rpm. And the direction of rotation of magnetic field depends on phase sequence. What is the phase sequence? And according to phase sequence, its direction depends. And we can change the direction of rotating magnetic field by interchanging any two-phase wire. We can easily reverse the direction of rotation of three-phase induction motor. So, when we gave supply to the stator winding of three-phase induction motor, a rotating magnetic flux created, and this rotating magnetic field cuts the stationary rotor conductor, and due to the change in flux linkage at the rotor conductor, an EMF is induced in the rotor winding according to the Faraday's law of electromagnetic induction. So, as we know that the rotor windings are short-circuited at both ends, so an induced current flow in the rotor winding. And according to the Lenz's law, this current tries to oppose the cause due to which it is produced. Since the cause is relative motion between rotating magnetic field and stationary rotor conductor, so rotor start rotating in same direction in which rotating magnetic field rotates to reduce the relative motion between rotating magnetic field and stationary rotor conductor. The torque that is produced as a result of interaction of these two magnetic fields, that is given by torque produced by induction motor, is K into BR, that is magnetic flux density of rotor, into BS, that is magnetic flux density of stator. So after discussing the working principle, there is a question: can the induction motor run at synchronous speed? Why? Normally, three-phase induction motor is also known as asynchronous motor. Why it is called asynchronous motor? Because it always runs at a speed that is lower than synchronous speed. Then what happens if at anyhow we can able to achieve rotor speed at synchronous speed? Then what happens? Can induction motor runs at synchronous speed? So its answer is no. No, induction motor does not run at synchronous speed. Why? If rotor runs at synchronous speed, so the relative speed between stator rotating rotor conductor and rotating magnetic field, relative motion will become zero, and rotor does not cut rotor. So rotor will appear stationary to the rotating magnetic field, and rotating field magnetic field will not cut the rotor conductor. So net induced EMF on rotor will become zero, and when net induced EMF will become zero, the current produced on rotor is also will become zero, and so induction motor does not run at synchronous speed. So when the speed falls, the rotating magnetic field will cut rotor winding and torque is produced. After discussing the working principle, now we will discuss slip. What is slip? As we know that induction motor will always run at a speed lower than synchronous speed. What is synchronous speed? In previous slide, we we were discussed that the speed at which rotating magnetic field rotates is called synchronous speed. So when we are discussing about the slip, it is defined as the difference between the motor speed and synchronous speed is called slip, and it is always expressed in percentage. So it is denoted by capital S, and S is equals to the ns minus nr, where ns is the synchronous speed of and nr is the rotor speed, or we can generally say that motor speed. So in percentage, we would write it as S equals to ns minus nr upon ns into 100, where ns is your synchronous speed, that is given by formula 120f upon p, and the current rotor current produced on rotor, so its frequency will be defined as fr equals to s into f, where s is called slip and f is called supply frequency. Notice that what if rotor runs at synchronous speed, what will be its slip? As we know that slip equals to ns minus nr, and rotor speed will become equals to synchronous speed. So ns minus ns will become zero. So when rotor runs at synchronous speed, its slip will become zero. And what happens if rotor is stationary? If rotor is stationary, then rotor speed will become zero, and the formula for s equals to ns minus nr upon ns. So nr will become zero. So ns upon ns will become 1. So if rotor is stationary, then the slip of induction motor will become 1. So slip region for three-phase induction motor is start from 1 to 0. So there are some numerical based on this formula. And first example is a 208 volt, 10 horsepower, 4 pole, 60 hertz star connected induction motor has full load slip of 5%. What is the synchronous speed of the motor? And second is, what is the rotor speed of this motor at rated load? What is rated load? When induction motor runs at 5% slip. What is the rotor frequency of this motor at rated load? So we have to find the value of ns, that is synchronous speed. And as we know that the formula for ns is equal to 120 f upon p. Here the data is given, frequency is 60 hertz, number of poles is 4, and full load slip is 5%. So ns equals to, as we know that 120 f upon p. After putting the value of f and p, we get synchronous speed equals to 1800 rpm. After getting synchronous speed, we have to find rotor speed. And as we know that the formula for slip equals to ns minus nr upon ns, and slip is given 5%. So motor speed nm equals to 1 minus s upon ns. So first we have to convert percentage slip into fractional slip. So after so slip will become 0.005. So motor speed equals to 1 minus 0.005 into ns. We get the value of motor speed equals to 1710 rpm. After getting the value of rotor speed, we have to calculate the value of rotor frequency. As we know that the formula for rotor frequencies is S into F, we get the value of S as well as F. So after putting this value, we get the rotor frequency, that is 3 hertz. And load torque developed by three-phase induction motor is given by formula P out upon omega m. So P out is given 10 horsepower. We have, as we know that the SI unit of power is not horsepower, it's watt. We have to first convert horsepower into watt by multiplying it with 746 upon omega m, where omega m is the motor speed, and motor speed omega m is calculated by putting the formula omega equals to 2 pi nm. And as we know that the nm is in rpm, so we have to convert rpm into rps, revolution per second. So we have to divide 2 pi nm by 60. And after putting this value, we get the torque produced by induction motor is 41.7 Newton meter. Second question is given here. A 220 volt, 3-phase, 2-pole, 50 hertz induction motor is running at slip of 5%. Here we have, in this question, the value of frequency is given 50 hertz, and we have slip, the value of slip, that is 5%. And after converting it into fraction, it will become 0.005, and number of poles is 2. So we have to find the speed of magnetic field in revolution per minute. Speed of magnetic field means we have to calculate ns, synchronous speed. And as we know that the formula for ns equals to 120 f upon p, after putting the value, we get the value of ns equals to 3000 revolution per minute. The speed of the rotor in revolution per minute, as we know that the formula nm equals to 1 minus s into ns. After putting this value, we get the speed of the rotor, that is 2850 revolution per minute. And then we have to calculate slip speed of the rotor, as we have the value of rotor speed and synchronous speed. We can easily calculate the value of slip speed of the rotor by putting this value, or we can calculate slip speed by putting n slip equals to s into ns. So we get 150 revolution per minute, or simply we can calculate it by putting the value of, we have s equals to ns minus nr. And the rotor frequency, the formula for rotor frequency is equals to Fr equals to S into F. And we have the value of S as well as F. We get it 2.5 Hz. So after discussing slip, we have to discuss what is torque slip characteristics of three-phase induction motor and how three-phase induction motor torque varies in different slip region. So the torque slip curve for three-phase induction motor gives us the information about the variation of torque with respect to slip of motor. So the formula for torque is equals to Ks R2 E square to 0 upon R2 square plus Sx to 0 square, where K is the constant, S is the slip of three-phase motor, R2 is the rotor winding resistance, E2 0 is induced EMF on rotor winding at standstill condition. Again, R2 is your rotor winding resistance and X2 0 is rotor winding reactance. And as we know that the formula for NR equals to ns 1 minus s, or we can say that s equals to ns minus nr upon ns. At starting, when nr will become 0, so slip of the induction motor will become unity. The starting torque will act on motor can be found by putting S equals to 1. So starting torque of the three-phase induction motor will become K R2 into E square 20 upon R2 square plus X2 S square X2 0 square. And when rotor speed of induction motor will equals to synchronous speed, at that condition the slip of the motor will become 0 and the torque act on motor will become 0, because when we put S equals to 0 in equation first, we get torque equals to 0. So torque slips, when we are discussing about torque slip characteristics curve of three-phase induction motor, it broadly divided into three regions: low slip region, high slip region, and moderate slip region. In low slip region, the value of S is very small. So the value of S square x to 0 square, Sx to 0 square is is very much lesser than R2 square. So we can neglect Sx to 0 square as compared to R2 square. After putting the value, we get torque in low slip region is directly proportional to slip. In second region, where high slip region, the value of S is considerably high. So the total value of S square x to 0 square is much higher than R2 square. So in second case, we neglect R2 square as compared to S square x to 0 square, because the value of R2 square is much lesser than S square x to 0 square. After neglecting R2 square, we find that in high slip region, torque is inversely proportional to slip. As slip increases, in high slip region, torque will decrease. While in case of low slip region, as slip increases, torque increases. The maximum torque is independent on rotor resistance. The motor will produce maximum torque when slip of motor will become equals to R2 upon X2 0 square. So this is the torque slip characteristics of three-phase induction motor. Here we saw that at low slip region when S equals to 0. When slip increases, torque increases, and after achieving its maximum value, and maximum value of torque we will get at when S equals to Sm, where Sm is the slip corresponding to maximum torque, and it is given by the formula S equals to R2 upon X2. After attaining maximum torque, when torque slip characteristics enters in high slip region, when slip increases again from S equals to Sm to S equals to 1, torque decreases there. So, what are the advantages of three-phase induction motor? In this slide, we will discuss about the advantages of three-phase induction motor. The main advantages of three-phase induction motor, as we are discussing first introductory part, its first advantage is it has simple and rugged construction. Its second advantage is it requires less maintenance, and its third advantage is it has high efficiency and good power factor. Next advantage is it is less expensive as compared to other synchronous motor or DC motors, and it has self-starting torque. That means we does not require any additional starting winding or starting three-phase induction. After discussing the three advantages of three-phase induction motor, we will discuss about the disadvantages of three-phase induction motor. So the main disadvantages of three-phase induction motor are as follows. Its first disadvantage is, as we know that the three-phase induction motor are constant speed motor, so the speed variation is a main problem. So their speed control is very difficult. If we want to operate induction motor at different speeds, so its controlling is very difficult. Its other disadvantage is three-phase induction motor have poor starting torque and high inrush current. What is inrush current? At the time of starting a three-phase motor, induction motor, the current drawn by motor is called inrush current, and it is generally 4 to 8 times of full load rated current. And its other disadvantage is they always operate under lagging power factor, and during light loads they operate at very worst power factor, that is about 0.3 to 0.5 power. These are the disadvantages of three-phase induction motor. After discussing all this, we have to discuss where three-phase induction motor are used. So first, it is used in pumps and submersibles. Second, three-phase induction motor are used as a pressing machines, in a lathe machine, grinding machines. Three-phase induction motor works as a conveyors. It can work as floor mills. It can work as a compressor. Thank you and have a nice day.